as I say, gamma is called the effective action. The thing I've called phi bar and called the mean field is sometimes called the classical field in the literature. Other questions? Now, as I said at the end of last lecture in a frenzy of enthusiasm, given any gauge field theory, this statement that, which I will call generically the word identity, because, as we will see in the course of this lecture, the conventional word identities, those of you who've seen the conventional word identities, are all consequences of it, and I'll in fact derive a few of them as time goes on, enables us to complete the renormalization program for quantum electrodynamics with or without a massive photon by showing that there is no need for gauge non-invariant counterterms. I will now give the proof. It's practically staring you in the face, but if you're not familiar with this formalism, you may not recognize it. So I will give the proof in detail for a general theory of this form, i.e., also, of course, consistent with the BPH program. That is to say, it is a renormalizable, it's a theory that involves only interactions of renormalizable type. We allow all gauge invariant interactions, but we don't allow any non-gauge invariant interactions. And there is a non-gauge invariant term of this form, but it is restricted to be quadratic in the dynamical variables or lower. Proof goes is a sequence of 5 statements. 1, I begin, it's an iterative proof. Assume only gauge invariant counterterms needed to order e to the nth, where e is some coupling constant. If I have 72 coupling constants, order e to the nth, lambda to the nth, etc. I now wish to prove that only gauge invariant counterterms are needed to order e to the n plus 1, the usual game. Firstly, what does BPH say? BPH says, if it's a theory with only renormalizable interactions, all divergences to order e to the n plus 1, that is, that come up in the next order of perturbation theory, if we've made everything finite to order e to the n, can be canceled by adding an additional term to the interaction. S goes into S, plus its term explicitly proportional to e to the n plus 1. The counterterms. You add the counterterms, and I'd better put n plus 1, so you will realize that this is a sum of counterterms computed to order n plus 1 with divergent coefficients, of course, depending on the cutoff. I haven't talked about gauge invariant cutoffs yet, but let's assume there is a nice cutoff that preserves all this. And this is, according to BPH, if we have only interactions of renormalizable type, polynomial in phi d mu phi of dimension less than or equal to 4. That's simply the general BPH result. We're working in 4 dimensions. Is everyone clear about that? They just say add the appropriate counter terms, and then you get rid of all divergences to the next order, and then you iterate along. And they tell you how to add those counter terms. And by the way, they tell you how to add them by doing a power series expansion at the point 0. There is a little technical sticking point here if we're dealing with electrodynamics with the massless photon, because there is the possibility of singularities at the point 0, because that's sitting on top of the photon mass shell. I will simply not worry about that in this lecture. I will assume we've given the photon a small mass. Then afterwards I'll consider the limit as the mass goes to 0. 3. What effect does this have on the effective action? Well, to order e to the n plus 1, adding the counter terms, goes into the effective action. I said I wouldn't use it, and now I say it, the generating function for IPI diagrams. Of course, you will add a term of order e to the n plus 1 that just comes from these terms you've directly added to the Lagrangian. They do generate IPI diagrams just by themselves. So you will add just replace phi by phi bar, just as if it were a term in the free Lagrangian. However, they will also appear as internal parts of other Feynman diagrams once you've added complicated Feynman diagrams once you've added these interactions. But since there's an explicit e to the n plus 1 in front, that's an effect of order at least e to the n plus 2, and maybe higher, since any complicated Feynman diagram has at least one vertex in addition to these new vertices you have added, and maybe more. Now, staring at this formula, we see for 2 order e to the n plus 1, before I add the counter terms, gamma phi bar is something finite, independent of the cutoff as the cutoff goes to infinity, minus e to the n plus 1, s counter term, n plus 1, of phi bar, because this theorem says the sum is supposed to be finite. All EPA graphs are finite. And therefore, since I can get rid of all the divergences by adding this thing, which has cutoff-dependent coefficients, all the divergences must be of this form. Now we use the word identity. These are, of course, this is a iterative proof, so perhaps I should have put primes on here to indicate that these are renormalized fields. We're now doing everything in terms of. I'm sorry, I should have done that earlier. Of course, it doesn't matter. Let those fields, how those fields phi are scaled has nothing to do with the proof of the word identity. The word identity tells us that if, and our iterative stat, we assume only gauge invariant counter terms needed to order e to the n, so the word identity is valid. The word identity tells us that, where this is some gauge transformation, tells us that this gamma down here, or prime, it doesn't matter, that this gauge transformation here is supposed to leave everything invariant except the quadratic term. Now, the quadratic term is certainly not divergent. It's 1 over alpha b mu prime squared plus u squared a mu prime squared. It's totally fixed and known. Doesn't have any power series expansion in E. Some fixed known thing.
Drops that box over to Children's Hospital. He has nothing coming back. Can he pick up the box at G building?
In the gauge invariant part.
Doug.
If the whole thing is gauge invariant, it'll be the cutoff dependent part.
Well, I say after he drops the box off at Children's Hospital, the open. The compactor box. Pick up the box at G building. Bring it in.
The whole situation.
And bring it in.
Is everybody happy with the argument? One step, usual practice. Notice the coming of this way of BPH. Word identity. BPH says that our neighbors are control the you get rid of the emergencies if you have contact with a certain source. Word identity. Return. No term, no full-time self-mass term. I think
Take the swap.
it's done the other way, in which this thing is first expanded out to get a whole sequence of complicated-looking equations for different mean functions, and then the difference of these equations is individually used to spin down one counterterm, possible counterterm of these. We find the sequence of the series, which is this way its clarity and simplicity. I will later expand this out to get the function interesting relations about individual functions, but it won't be concerning the divergence. But after all, it's a very rich equation. It's also such nice things about the divergent parts of the function. It could also say nice things about the finite parts of the function. So we'll come to that later. Are there any questions? The argument is so simple, you need to see if you want out of this report Now let's do a particular thing. Let's do massive electrodynamics with the massive
Mike, they called it 145 for a swap on the compactor. That's not the one at G building. G building's the self-contained, right? Yeah, 10-4, that's got to be it. Okay.
and the coupling constant and counterweight. That's the divergence.
So 2 to 7, Sully.
Then I have side by side, I slash H prime. These two terms come together as a consequence of gauge invariance. It's not totally in my earlier discussions with many of the terms I wrote down there. I put 0 on this board, and therefore bottom. identity asserts that that has no radiative correction, no countercurrent radiative. That remains the same. It stays that way. And then they will find at zero momentum, and that has no corrections. This includes all possible gauge invariant counterterms of order of dimension less than or equal to 4, and is therefore a strictly renormalizable Lagrangian. It gives you finite answers for appropriate cutoff-dependent choices of the counterterms A, B, and C to every order in a power series expansion in E. Now, of course, once we have this expression, either exactly because it has come down to us from heaven on a golden tablet, or by the result of tedious labor to some finite order and perturbation theory, we can write this in terms of unrenormalized fields and define the bare charge as masses, values of alpha, and coupling constants. The unrenormalized fields, indicated without a prime, are scaled, so their kinetic energies, the derivative terms, are of standard form. They then have a interaction. Well, I'll write up the whole thing. Minus E naught, unrenormalized A slash, minus M naught psi. That's the definition of the bare charge and the bare mass. Yes, we'll shortly see there's a bare alpha, but it's trivially related. Is it, what?
To read the question, I have one question about the number of time functions on the L. It says that you have a wave function renormalization pattern function A, one for the side, and one for the, and a mass pattern, right? But you haven't really discussed the charge renormalization.
That comes in automatically. This term always comes in this combination. If there were a different coefficient for this and this, then we'd break the gauge invariance. We'd have a non-gauge invariant term appearing in our Lagrangian that was not one of our original quadratic terms. It all takes care of itself. This is a well-organized talk, you will see. Okay. This is the consequence of gauge invariance, that these things always come in together. There it is. Okay? If S counter term of phi bar has got to go into S counter term of phi bar under a gauge transformation defined with some number E, which is the number that appeared in the starting Lagrangian in the BPH sense, because that's the gauge invariance that keeps iteratively reproducing itself. Therefore, this term has got to come with this term. Also true for spinor theory, where it's much more complicated if you try and work it out graph by graph, because there you've only got to balance the kinetic energy against the A mu phi star phi interaction, but also against the A mu squared phi squared interaction. Likewise, they've got to come in exactly the combination they occur in the free Lagrangian. Otherwise, this result, which I just proved for you, would be false. Okay? It's good. It's a good way of doing things. Okay. Of course, when you actually do a computation, it's as complicated as any other. Now, plus the bare photon mass over 2 A mu squared. We also define the quantities Z3 and Z2 by as the quantities that give us a scale between psi prime. Well, I'll do it this way. Psi equals Z2 to the 1/2 psi prime, and A mu prime equals Z3 to the 1/2, A mu equals Z3 to the 1/2, A mu prime. There is a Z1 that occurs in traditional treatments of electrodynamics, which I'll never talk about. It's something else that you show is equal to Z2 because of gauge invariance. That's just the question I just answered for you. Okay. Now, by comparing these, I should make a remark on the gauge dependence of these things, or since we're working in a theory with a massive photon, the alpha dependence of these things. As you recall, when I switched from one value of alpha to another by introducing an auxiliary field, that did not involve any redefinition of A, although it did involve a redefinition of psi. Therefore, we'd expect Z3, which doesn't get redefined because A doesn't get redefined when we switch when we introduce this auxiliary field, to be alpha independent, or in the massless case, gauge independent. Z2, on the other hand, might well be alpha dependent. Don't know. We also expect the bare masses of the particles to be alpha independent. After all, they're masses. How can they depend on the gauge? Okay. And an interpolating field may depend on the gauge. It may be a different operator in one gauge than another. But a mass is a mass, physically observable quantity, and also the charge. Because of this fact, there is a curious consequence, although I will not go through a whole song and dance of deriving the spectral representation for a vector field. It follows essentially the same lines that it did for a scalar field. One can use positivity of the spectral representation, positivity of the weight function, to show that Z3 is less than or equal to 1, our usual result. On the other hand, Z2 is defined in the terms of the psi field, which, as you recall, is the original psi field we started out with in a nice theory with positive definite quadratic forms and so on, positive definite metric in Hilbert space and so on, times an exponential of this preposterous field with minus signs in its propagators and negative metric intermediate particles and God knows what else. And that may screw up the positivity of the spectral formula for the spinor field. So you don't be surprised if you're ever doing a computation and you compute in one of these gauges Z2 and discover it is larger than 1. For some values of alpha it's larger than 1, for some values of alpha it's smaller than 1. That's just because it's mixed up. When we've made the change of fields, we've mixed it up with this auxiliary field, so there can be negative weights appearing in the spectral weight function. Now, those are just little comments, but now let's work out what these things are. This is straight algebraic substitution. We find, let's see, have I got this right? Yes. 1 plus A equals Z3. 1 plus B equals Z2. Just comparing these two expressions, which are supposed to be equal. That's rather uninteresting unless you happen to know A and B and wish to compute Z1 and Z2 or otherwise. Looking at this term and comparing it with this term, we see E A slash prime must be the same as E naught A slash, and therefore E equals Z3 to the 1/2 E naught. That's a very interesting equation. I'll get back to that. We also see M naught equals M plus C times Z2. That's not particularly interesting, and I won't say anything much about that. This is an interesting one. I'll put a check on it. Let me just read them off rather than trying to derive them. Mu naught squared Z3 equals mu squared. That's also going to be interesting. And alpha naught equals Z3 alpha. That's also essentially uninteresting. Now, two of these equations I've identified as interesting. One is One is mu naught squared Z3 equals mu squared. This implies that as mu squared goes to 0, mu naught squared goes to 0, unless Z3 develops a pole, a rather unlikely possibility. Maybe some logarithms because of those intermediate photons, but a pole is rather strong. That means, of course, that we regain the massless R equivalently. As mu naught squared goes to 0, mu squared goes to 0. Either way you want to say it. If you give a 0 renormalized mass for the photon, you get a 0 bare mass, and if you give a 0 bare mass, you give a 0 renormalized mass. The masslessness of the photon is a statement that is preserved by renormalization. The other equation is E equals Z3 to the 1/2 E naught. This is an important equation because it represents the universality of charge renormalization. If I had a lot of different fields, which may have a lot of interactions that are not written down here, some of them have strong interactions between them and others don't. Say it's the theory of electrons and protons. And the protons are interacting with mesons and doing everything else. It's only laziness that kept me from writing down a theory with 42 Fermi fields, and then I would have gone through the same thing, and I would have discovered that if they have the same E's, they have the same E naughts, because the only thing that appears is Z3, and Z3 does not have nothing to do with the Fermi field and its renormalization. It's just a quantity having to do with the photon. They may all have different interactions and therefore different Z2s, but they're all going to have the same Z3 on account of there's only one Z3, there only being one photon. Thus, if particles have the same bare charge, they have the same renormalized charge. This is reassuring because you remember I raised this as a question last week when I said, why is it that the proton and the electron seem to have exactly the same physical charge? If their charges were renormalized differently, if the renormalizations of the electric charges of the proton and the electron depended on the fact that the proton has strong interactions and the electron did not, God would have had to have been incredibly nice to adjust the bare charges in just such a way that the physical charges came out equal. He doesn't have to be nice, he just has to be simple-minded. If he says the bare charges are equal, then it automatically comes out that the renormalized charges are equal. Indeed, if he had said the bare charges were one of them 3 times the other, the renormalized charges would have come out being 3 times the other. The ratio of the renormalized charges is the same as the ratio of the bare charges. We've obtained this by an elegant but rather abstract argument, but we can understand it physically. Suppose we have a particle in a box, and we wish to compute the expectation value of the electric charge. Suppose it's a proton. Well, we say we know how to compute things from expectation values of operators from non-relativistic quantum mechanics. We expand the actual eigenstate of the system in terms of eigenstates of the non-interacting system and evaluate the operators in that expansion. At first glance, that looks very complicated because the proton could be a bare proton that would contribute charge 1, and then it could be a bare neutron and a bare pi meson, but that would also, et cetera, 14 nucleons and antinucleons and a lot of mesons around. But we really don't have to need to know this expansion because anything the proton can virtually become is also a system of charge 1, a consequence of charge conservation, and how electric charge differs from pseudoscalar coupling constants, by the way, for which a similar result is not true. Consequence of charge conservation, everything it goes into must have charge 1, can never be found as a neutron and a pi minus, bare neutron and bare pi minus, and therefore the expansion doesn't matter. The total charge in the box is 1, no matter what the proton's wave function is, because it's a superposition of things with charge 1, or charge E naught, I should say. This argument is very comforting, but on this level it makes you a little bit nervous because that would indicate that there is no charge renormalization at all. And here we definitely see one with the Z3 to the 1/2. What happens there? Why is that so? Well, it is because we measure the physical charge. I'll give such a Gedanken measurement shortly. We measure the physical charge by going far from this box and looking at the long-distance behavior of the electric field. far away from the box. That's how we measure the charge. We don't really construct a J0 measuring operator and stick it inside the box. We look at the electric field at large distances. Now, in a field theory, the vacuum has some of the characteristics of the vacuum is a dielectric. What is a dielectric? A dielectric is an object such that when you impose a constant electric field, there is a correction to the expression for the ground state energy of the system. It is not good old Maxwell's 1/2, 1/8 pi more usual units, 1/2 in our units, E squared. It's 1/2 E squared plus corrections. That's what makes it a dielectric. Of course, in a field theory, if I impose a constant electric field, there's all these complicated bubble graphs and so on computing to the energy, and the vacuum will have dielectric properties. Now, if I put a charge in a dielectric, as Faraday knew, if I put a charge in a dielectric, it is shielded. How much it is shielded by depends. If you look at the electric field at large distances, it is not the charge you put in the dielectric, because the dielectric tends to polarize, right? You put a big positive charge in the middle, and the dielectric, depending on its dielectric constants, those are little dipoles in the dielectric, polarizing, attracted to it, and shielding the charge if you're within the dielectric. Of course, if you're outside the dielectric, the missing charge appears on the surface of the dielectric. But we are not outside the dielectric. We are not outside the vacuum. We swim in the vacuum like fish swim in the sea. And therefore we're in the Faradayan situation inside the dielectric, and we see the charge is shielded. Of course, this does not depend on the internal constituency of the charge you put in the dielectric. It is a universal result that only depends on the dielectric constant of the medium, which we can now interpret Z3 as being the dielectric constant of the vacuum. Notice, by the way, it is charge shielding. Z3 is less than 1, and therefore E is less than E0. It doesn't, dipoles don't align themselves the other way in the dielectric, and Z3 is not greater than 1. Okay? That's, of course, just a bunch of metaphors I've laid on you. No one would accept that as a convincing argument, but I hope it enables you, it's easier to hold in your head than the long argument we've gone through, which I hope is convincing. Now, are there any questions about any of this? All of the answers are perfectly standard. You can find them in Dworkin and Drell or Schwaber or Luria or any other standard book. The methods are patent invention, none genuine without this photograph. Okay. Now, I've been concentrating on the electrodynamics of charge spinors. I should say a few words about charge scalars. The whole story is pretty much the same, except for a technical detail. There is one gauge invariant counterterm of dimension 4, which is needed in a charge scalar theory, which might be needed in a charge scalar theory, and which is not there in a spinor theory, and that is psi star psi squared. That is of dimension 4. That is gauge invariant. Therefore, you need a in order to generate such a counterterm as a redefinition, you need a lambda naught. It's 8 conventionally for combinatoric reasons. You need a lambda. You need a quartic interaction of the. Is it 8? Yeah, I think that doesn't matter. Whatever it is. Well, you need a quartic interaction of the scalar charge scalar particle with itself in order to have a strictly renormalizable theory. The electrodynamics of charged spinor particles is a one coupling constant theory. There are masses in the theory, but the only dimensionless coupling constant is E. It's a one-parameter, one-coupling constant theory. The electrodynamics of charged scalar particles, in order to be renormalizable, is a two-coupling constant theory. You have to have a scalar self-interaction. In fact, you can easily see where it comes from. If you consider, here's a charged scalar scattering off another charged scalar, or an antiparticle, I guess, as I wrote it. They have a direct interaction with the photon, a mu squared. I picked this graph because it's an exceptionally simple one and that it has no derivative couplings in it. The integral is obviously proportional to d4k over k fourth at high k. 1 over k squared, 1 over k squared, no derivatives. That does produce a logarithmic divergence, and you need the renormalization of this coupling constant to cancel it. That's not a golden argument because there are lots of other graphs in the same order, and it requires a little checking to show they don't cancel among themselves, but they don't. Yes?
I know that these Philly theories would it be consistent theories to renormalize that kind of graph to do?
Yeah, sure. That's the same thing. This is exactly parallel to the phenomena we ran against when we were discussing the renormalization of Yukawa theory, where again we couldn't just write down where G psi bar gamma 5 psi phi was not strictly renormalizable. We also needed lambda phi fourth. Okay, and you could do the same thing. Sure, you can set those graphs equal to 0. At what point you wish to set them equal to 0? The point 0, some well-chosen Euclidean point on the mass shell, of course you'll get completely different theories. You have your freedom to set them equal to 0. It's a free parameter. Okay, but I mean, it's like you could also set them, it's like setting it's just a totally arbitrary act. You can set them equal to 17. What you can't do is set the bare coupling constant equal to 0. Yes?
Are there any two methods like in some of the common coupling constant theory, like the argument that systemic determinants
Yes, weak. The only charged mesons we know of also have strong interaction 5/4 couplings. So that's not a particularly good idea. But suppose there were a scalar muon, a particle that only had electromagnetic and weak interactions, okay, and was charged, okay, that it was observed. Then you could get this thing by you get the 5/4 coupling, the nice way of defining it, not from the viewpoint of combinatoric renormalization, not from the BPH viewpoint, but the viewpoint of making it an observable quantity, is to make it equal to the 4-particle IPI Green's function with all 4 external lines on the mass shell at the symmetric unphysical point S equals T equals U, as in a test problem, you may remember. Okay? And if you do that, of course, it's direct use observable via dispersion relation, and one can observe it. Okay. The strong interaction pion 4-pion coupling constant has been measured in that way, exactly that way. While it's not quite that good, we don't have pion colliding beams. You have to be a little bit indirect. You do pion off nucleon goes into 2 pions plus a nucleon. I see I've made my initial states on the left violating my own convention. Okay. Since you don't have pion targets, you've got to get around that somehow. You have pion beams, that's no problem. And then you can go to a kinematic region where you can extrapolate to this pion pole here. And then the residue, you already know the pion-nucleon coupling constant, so the residue of the pole is the pion-pion scattering amplitude, and then you have a way of measuring pion-pion scattering without a pion target. Okay. It's not as accurate a way as you would if you had a pion target, but, I remember they were doing these experiments at CERN 4 or 5 years ago, and they were swearing up and down. They were producing tables of pion-pion phase shifts with error bars and everything else. It looked good.
Rotating railway, don't mention the side squares.
That is a lapse if they do not. It is necessary for the theory to be renormalizable.
You mentioned the strong interaction.
The same thing. Other questions? Good time to ask questions. Yep. One of them very briefly. After all of these arguments make sense only if we have a way of introducing a coupling constant that preserves a coupling constant, a cutoff, a high energy cutoff on our Feynman integrals in such a way that gauge invariance is preserved. One method about which I will say nothing except to tell you it exists, I've discussed it in an earlier lecture, before we got to vector particles, is dimensional regularization. Ella Veltman and Hooft and Serlin and friends, as I learned during that lecture. Dimensional regularization fairly obviously preserves gauge invariance, because dimensional regularization comes from starting out with formal Feynman integrals for integral dimension and then unambiguously continuing them to complex dimension, whereupon the divergences become poles. Any property that's true for integral values of the dimension will be evidently true for the analytic continuation. This is an unambiguous analytic continuation. And in particular, gauge invariance. There's nothing about gauge invariance. You can't write it down in 72 dimensions. The fields will have more indices and everything, but you'll still have gauge invariance. Nothing special of 4 dimensions. That's a sort of swindly argument, but it nevertheless turns out to be right, and I'm told that those who want a detailed proof looking into the guts of Feynman diagrams can go to Ed Hoof's lectures, where he's been talking about matters of this kind. Am I right? Yes. Well, that's you either get an argument you don't believe or an argument you don't understand when it comes to dimensional regularization. Dimensional regularization. That's the nature of the subject, I fear. That's right. All arguments fall into 2 classes: those that are incredible and those that are incomprehensible. and these classes are not mutually exclusive. Okay. The second method, which is somewhat more old-fashioned, but worth talking about because it's cute and it's easy to show that it works okay, is a method with regulator fields. Due to Pauli and Villars. You recall our old method of regulator fields was basically very simple. We took a Lagrangian that was L0 of a free field plus some interactions, including all the counter terms and everything else. And we added to it, we wrote this one instead. L0 of phi plus L0 of phi 1. Perhaps there would be several of them if we had super bad divergences to worry about. Plus L prime of phi plus I phi 1. Where phi 1 was a very heavy field. Did I make some mistake? No. Okay. The result of this was to turn 1 over k squared minus mu squared into 1 over k squared minus capital M squared, and in all the propagators. So the result was just to subtract propagators. So that every time you had a graph with a propagator in it, you subtracted the propagator with a very heavy mass. And then all our integrals became convergent, or if one heavy mass wasn't good enough, we'd subtract 72 of them, appropriately weighted, and then all of our integrals became convergent. To make it a minus sign in the propagator, and also make it an unphysical theory. There is no physically realistic finite theory known to man other than free field theory. Some renormalizable, lots of non-renormalizable, no non-trivial finite ones. Of course, we can do exactly the same trick as far as the photon, massless or massive, goes, with no problem insofar as the photon goes. I'll just write down the same thing. Mass m, same gauge, of course, same alpha parameter. There's no problem there. That doesn't affect the gauge invariance of anything. It just adds something to a mu, so it adds something to a mu, period. However, we run into troubles, as Pauli and Villars pointed out, if we try and do the same trick for the charged particles, let us say the fermion in the theory. And we have to do that because one encounters a lot of graphs that are divergent and only contain fermion propagators along the loop that's responsible for the divergence. So no matter how nice we make the photon propagator, that's not going to do anything to the divergence in that graph, or to the divergence in this graph. This one is awful. It's quadratically divergent. This one is just logarithmically divergent. Now, if we try and do it in the same way, say by turning psi bar gamma mu psi into the object that appears in the interaction, into psi bar plus I psi 1 bar, I should put a minus sign here, gamma mu psi bar plus I psi 1, and I should have put that one upstairs to be consistent. Then, of course, we've made everything finite, but we've also totally destroyed the gauge invariance, or even the conservation, to hell with gauge invariance, we've destroyed the conservation of currents, because the divergence of the cross terms in this object is not zero. It's proportional to the difference of the masses of the two fields. So that's disgusting. Not only have we broken gauge and current conservation, we've broken current conservation in a disgusting way, where the larger we make our cutoff, the more severely we've broken current conservation. Pauli and Villars thought up the clever trick that takes care of this. What they do is as follows. They don't subtract the individual fields. They subtract, with appropriate coefficients to take care of all divergences, the currents, which certainly preserves current conservation and gauge invariance. It's now just a bunch of fields minimally coupled. And now the psi i's, I shouldn't have called them ones, I should have called them i's. Now, of course, there's no I in the coupling constant, so you may wonder what is going on. You choose the psi i's to be heavy fields, heavy masses, obeying Bosch statistics. It's sort of like our ghost trick of earlier lectures, except now we introduce Fermi fields obeying Bosch statistics, whereupon before we Dirac fields obeying Bosch statistics, where before we introduce scalar fields obeying Fermi statistics. We are mad with power. We can do what we want. Now, the result of these things obeying Bosch statistics is that, of course, you don't have the Fermi minus signs for loops. That's of course, also the result is that it's a totally unphysical theory with negative energies, but hell, it's just a cutoff procedure. You don't have the minus signs for the Fermi loops. So the contributions from these things come in with the opposite sign to the thing on the board, and therefore by appropriately adjusting the CIs, you can make all the divergences cancel. Thus, the full regulator field description for putting in a gauge invariant cutoff in they're perfectly, you can't tell the difference. You never have one of them in an external line or an internal line. They only appear in closed loops. So it doesn't matter. They're just regulator fields. You don't care what the probability of one of them scattering is because you're going to send this mass to infinity. Okay. For photons, subtract heavy propagators in exactly the way described before. But for fermions, you don't do a thing with the propagator. You just break up the graph into contributions from individual Fermi loops. For the charged particles, you of course play the same trick with charged bosons. There you introduce ordinary ghost fields. For charged particles, subtract, not on the level of the propagator, but on the level of the charged particle loops, subtract heavy loops. It's a little bit less clean to describe than subtracting propagators, but it has the great advantage that it preserves gauge invariance. In fact, you are going to do this part of the lecture. I don't expect you to pay too much attention to because you're going to work it all out. It's the current homework set. I ask you to compute the photon self-energy using both of these regularization methods, once for the spinor case and once for the scalar case. No, it's actually simple computations, and you will learn things by doing them. And they're historically important, but I've written out, in a spasm of creativity, I wrote out a little historical note on the problem set, so I won't say it in the lecture. Are there any questions about these regularization procedures? Oh, I will say that historical thing because it's so amusing. In the late 40s, there was a great problem with the self-mass of the photon. Ward had not even written down the very first Ward identity. But people knew. People didn't have any deep understanding of gauge invariance at all. They were still plugged. Schwinger was plugging along in Coulomb gauge. Schwinger and Feynman were the only two people who were able to renormalize quantum electrodynamics. They had the great secret. Schwinger was plugging along in Coulomb gauge because he knew what he was doing there, and Feynman was working in Feynman gauge because he didn't care if he knew what he was doing as long as his answers were consistent. However, they both knew that you shouldn't have to put in a mass for the photon because that would break gauge invariance, even if they weren't quite sure how to precisely formulate gauge invariance. And they both found, when they computed this graph, that they got they needed a photon mass counter term. And that caused a great deal of irritation. Both of them made nervous remarks and swept it under the rug and said, really, we have to set this equal to 0 by gauge invariance, and quickly went on to computing something observable. And well, yes, Schwinger says, I don't know what Feynman says. Schwinger actually says in one of his early papers, Roy was around then, you can remember, he says, we just set it equal to 0 by gauge invariance. It's divergent and therefore ambiguous, and we set it equal to 0. Yes, well, he was very nervous, but they were they were nervous remarks. And then Pauli and Villars, I think, really clarified everything by inventing, oh, Roy's going to fall on me. I've destroyed history, huh? It's not that way at all. Stalin was not present in Besieged's Winter Palace. Okay, there's a false historical remark here. As I learned that it was greatly clarified by the realization that you could systematically put on a cutoff procedure in a gauge invariant way and then explicitly and unambiguously compute it and find it was 0, the photon self-mass. Now, the last topic I would like to take up in this lecture, I won't get to the anomalous moment of the electron until next lecture. It turned out I had more to say than I thought I did at the end of the last lecture, is some consequences of the Ward identities, of the Ward identity for individual Green's functions chosen to be of particular interest. Well, period, I guess. Doesn't the sentence just ran off into the sand? So for convenience, we'll stick to spinor electrodynamics. I will drop, in order to avoid hideously complicating my equations, well, firstly, let me write down the Lagrangian. Rules are conventional gauge invariant Lagrangian plus 1 over 2 alpha d mu a mu prime squared. And I'll put in a mass term plus mu squared over 2 a mu prime squared with the photon mass. I'll write down the gauge transformations explicitly because I'll now need them explicitly. Delta a mu prime equals a mu prime plus delta chi. Delta psi prime equals, sorry, it's just delta chi. Yeah, it's just d mu delta chi. Now that's right. Delta psi prime is minus IE delta chi.
Look, when he called in, Jimmy, that he wouldn't be in today, but he'd be in tomorrow.
Delta chi. And we know our Lagrangian must be gauge invariant except for, the gamma must be gauge invariant except for an addition. That's just the integral of the explicitly displayed term. To keep from writing equations with primes and bars and everything, and double bars on the mean field version of psi bar, I will just drop primes and bars from now on. You will know I'm talking about renormalized mean fields. Just to get some I will introduce a systematic notation. I will have a lot of Green functions to worry about. So we'll refer to gamma n, m, where this is number of psis, which of course equals in the number of psi bars, unless it's a gamma that's trivially 0. And this is the number of A's. Just so I can able to tell one Green's function from another. These objects, of course, will depend on a bunch of position variables, or their Fourier transforms on a bunch of momentum variables, and if they involve A fields, they'll also have tensor indices associated with the A fields. For example, the propagator, the lowest order, is minus I over k squared minus mu squared, dropping the I epsilons, g mu nu minus k mu k nu over k squared, plus I over alpha k squared minus mu squared, k mu k nu over k squared. Both the transverse and longitudinal part have mass mu squared, but the coefficient of k squared in the longitudinal part is 1 over 2 alpha. This makes it easy to compute gamma 002 mu nu twiddle. I'm glad I didn't put in bars and primes, much to write, which is a function of only one momentum k. The two momenta are equal. It's the photon self-energy, if you wish. It's minus k squared minus mu squared times the transverse projection operator plus alpha k squared minus mu squared times the longitudinal projection operator. Actually, for a massive photon, the most convenient gauge is Feynman gauge, alpha equals 1, because then the pole at k squared equals 0, which would otherwise give you mild technical problems, cancels between this term and this term. Although for certain purposes, Landau gauge is nice also. Now, this will, of course, be plus corrections of order E and higher, and we wish to study those corrections. The way we study those corrections is by writing out gamma in terms of its expansion in terms of the fields. The term that involved this object is the term bilinear in A. And therefore it will be a mu twiddle of k, a nu twiddle of minus k, because one momentum is going in, the other is going out, and we've suppressed the delta function, gamma mu nu twiddle 002 of k. That's the definition. It's that term in the expansion of gamma. And I guess I should put in a 1 over 2 factorial because it does involve two identical fields. Now, the gauge transformation on the class, these are of course supposed to be barred and prime, but I'm not going to write barred prime twiddle. I'll go bananas. The gauge transformation under which delta gamma equals delta of the gauge, well, equals delta gamma at equals 0. That's an easy way of writing it. Just the part there that suffers no corrections of order E. When a mu twiddle of k goes into a mu twiddle of k plus I k mu delta chi twiddle of k. In particular, this term must be unchanged, differentiating with respect to delta chi and integrating by parts. Well, I don't have to integrate by parts. I'm already in Fourier space. I deduce k mu gamma mu nu twiddle 002 equals k mu gamma twiddle mu nu 002 evaluated at E equals 0. Adding a term proportional to k mu to chi makes no change beyond the change that's already present in the 0th order. And that means that this object, the kernel in here, must obey this equation. Thus, all the corrections, all possible IPI graphs beyond the 0th order term, beyond the term that's already there, must contribute only to the part proportional to the transverse projection operator, an important consequence of gauge invariance. Lorentz invariance would tell us that this is a sum of two terms, and this one will get corrections that's a complicated function of k squared, and this one will get corrections that is another complicated function of k squared. The word identities, on the other hand, tell us only this term is corrected. This term just sits around. So whatever it is, and you're going to be asked to check this interesting result on the problem, is proportional to g mu nu minus k mu k nu over k squared. In fact, we can do even better because this expression has a pole in it at k squared equals 0. And we shouldn't expect to find a pole because we haven't got any massless particles in our theory. This is massive electrodynamics. Indeed, even if the photon is massless, we shouldn't expect there to be a pole because this is an IPI graph and we've taken out the one photon pole. So I can even say it's proportional to this thing times k squared to avoid that spurious pole. I'm saying delta gamma can't change. or acquires only a change due to this gauge fixing term, this term up here, when I add a divergence to A. Okay, if you like, you can think about it in position space. I add a gradient to A, integrate by parts. I pick up a term proportional to the divergence of gamma, which is multiplying by k mu in momentum space. Since there ain't no change beyond the change in the zeroth order term, k mu times gamma mu nu, a function of k, must be just the zeroth order term. Okay? This is, by the way, of the typical form of an equation we would get from that thing I discussed, but then rejected, reducing the ward identities from current commutators. The result, however, I emphasize again, all the corrections to the IPI, to the photon self-energy operator, are purely transverse form. From this already, I mean, if we didn't know it already, from this it would be lightning to deduce that, lightning rapidity to deduce that there was no photon self-mass term. But we've already deduced that, so why bother to go through it again? Of course, the photon self-mass term would require a correction proportional to g mu nu. Now let's go on and study a more complicated expression. I'll study the term proportional. Boy, I had troubles with my indices here. Well, I can figure out what I'm writing. Involving these should all be barred and primed. We normalize mean fields, but you won't catch me writing psi bar bar prime. Gamma 1, 1, 0 of x and y plus integral d4x, d4y, d4z, psi bar x, psi of y, a mu of z, gamma 1, 1, 1, mu. I'll write it in position space this time. I'm plus, of course, a lot of other terms. But as I'll show, these two terms mix up with themselves under gauge transformations and the other terms don't. Now, I'm now going to apply an infinitesimal gauge transformation. Since it's obviously not going to generate an a mu squared term, the infinitesimal gauge transformation applied to these two parts together, this one will give me a coefficient of psi bar psi, and this one will also give me a coefficient of psi bar psi, because a mu just picks up a term proportional with d mu chi. Therefore, the coefficient of psi bar psi after I make this change must be 0, because I know the result after making a gauge transformation is just to give me a term linear in a mu bar, which has no psi bar psi term in it. Thus 0 0 of x and y, I chi of y minus I chi of x. That's what I get from changing the first term. Then from changing the second term, I've got another integral, which out of slovenliness I'll just write inside my square bracket. Make this a curly bracket. d4z, d mu chi of z, gamma 1, 1, 1, mu, And no a mu, because a mu has gone into a mu plus chi, and I should call these delta chi's, I apologize. That must be 0, because that's the only psi bar psi term we get by applying a gauge transformation, and the whole thing has got to be gauge invariant except for the a mu squared term. Is everyone happy with this argument? Now, extracting the coefficients of psi bar psi and delta chi, for which I have to integrate by parts, I obtain an equation which says I gamma 1, 1, 0 of x and y delta of x minus z. That's what I get when I variationally differentiate this with respect to delta chi of z. Delta of y minus z minus delta of x minus z equals, and here I've got a minus sign from the integration by parts, so I'll bring it onto the other side, d mu gamma mu 1, 1, 1. Is there any question about the derivation of this equation? I simply have applied a gauge transformation to the action, used the Ward identity, and said that the gauge transformation can have no effect on this kind of term. This is, by the way, extraordinarily similar to the equation in structure to the equation we got before by manipulating the canonical commutation rules when we differentiated a current in two fields. Except it's not a current, it's an a mu. It's not a full Green's function, but it's a one-particle irreducible Green's function. It doesn't involve unrenormalized entities. It involves renormalized entities. But aside from that, it's the same equation. Now, let's use that in, let's go into momentum space. In momentum space, this is the Fourier transform of the one-particle irreducible three-point function. I'll assign my momentums rather more conventionally. I'll call these p, p prime, and k. And instead of all going in like in the general thing, I'll write this object as such that p plus k equals p prime. So p prime goes out while p and k go in. I'll call gamma mu twiddle, just to keep from 1, 1, 1, of p prime, p, and k. I'm getting tired of writing those 1, 1s, 1, so I'll just write it as gamma mu of p prime, p, P and K, dropping some symbols. That'll be, you can remember they're there for the rest of the discussion. Likewise, the other object with the P there, which is, of course, gamma 1, 1, 0, a function only of a single momentum. We already have notations for that. That's the renormalized photon propagator at p slash inverted. It's also, of course, equal to renormalized electron propagator, forgive me, gamma 1, 1, 0 p split. Now, when we take the Fourier transform, it's tedious to take it by hand, but it's easy to see the general, I'll just write down the answer. It's easy to see what the general structure will be. The only interesting question is what happens when we've got those delta functions here. If I take integral d4z e to the I p dot x e to the I p dot z, k dot z, delta 4 of x minus z, I get e to the I p plus k dot x. Therefore, the terms with the delta functions in them will give me terms where the momentum carried by the propagator is either this momentum or this momentum, either p plus k, which is p prime, or p prime minus k, which is p, depending on the order I do it. Therefore, rather than doing the Fourier transform out, I can obviously just guess its form, except for where the i's goes. I'll fix them. I'm a lazy man. I'll just write it down with a free constant in it and then fix the constant instead of doing the dumb Fourier transform by demanding that the equation be right to 0th order in E. So I don't have to worry about possible sign errors. I've got an equation like this. Ooh, I left something out. Someone should have called me. Way back here, I made a mistake. There's an E in here, huh? It's E pi. Very important. E here. Yeah. Minus I, that's the constant I dropped. You're right. Minus IE S inverse prime of P prime slash minus S inverse prime of P slash equals, I'll write it down and then I'll show you the constant is right, K mu gamma mu of P prime, P, and K. Now to check that I wrote you the answer with the right constant, I'll check it to leading order. Maybe I wrote it with the wrong. Yeah, there's a thumbtack sticking out of this thing. Let's see. My I S inverse minus I S inverse of P slash equals P slash minus M, the lowest order. Gamma mu equals minus E gamma mu to lowest order. That's minus E J mu A mu in our Lagrangian. Therefore, to check that I've got the right sign, I put in I put in minus E P prime slash minus M minus P slash plus M S inverse is P slash plus M over I. P slash minus M over I. S is I over P slash minus M. I times S is P slash minus M, and I've got a minus E. I make a lot of mistakes, but it's not true that everything I write down is a mistake. Was minus E K slash. Of course, this term cancels this term, and P prime slash minus P slash is K slash, so I did write it down with the right signs. Now, this thing has consequences. One of the consequences can be easily seen. The most striking consequence is if this is, by the way, the original Ward identity derived by Ward, although Roy may again call me and tell me it was really derived by Chilean. This is it. This is the form in which he had it. This is the original Ward identity. We can obtain a consequence by differentiating it with respect to K mu at K mu equals 0, fixed P. Okay? P prime, I remind you, equals P plus K. Differentiating the left-hand side, the second term contributes nothing. The first term contributes minus IE d by dp mu, since P prime is P plus K, S prime inverse of P slash. That's the result of the first term here, and since I've set K equal to 0, I've set P prime equal to P. The right-hand side is even simpler because when I differentiate this with respect to k mu, I just pick up the gamma mu. Differentiating the gamma mu gives me nothing because it's multiplied by k mu, which is going to 0. No prime here since p prime is p plus k. This is an amazing result. It says that gamma mu for a zero momentum photon is known completely in terms of the propagator. How could you be, what a surprise. It just comes out of gauge invariance, just comes out of the Ward identity. We can see how we can get this, how this leads to the result we earlier got much more cheaply. I'm going to talk for 3 more minutes and that's all. The early result we got much more cheaply about the conspiracy of counter terms. If we're computing in some order of perturbation theory in which to compute the counter terms, we write S inverse of P slash in a power series, A plus BP slash plus order P squared. This term is the term that fixes the psi bar ID slash psi counter term. Likewise, we can write gamma mu of P prime Pk equals C gamma mu plus order P plus order K. We expand that about 0 and just keep the constant term. And this fixes this counter term. Right? Everyone sees that. Now, applying this equation to these terms, we see that to get the derivative with respect to P slash, to P mu, we have minus E gamma mu, now evaluating this equation at P slash equals 0, after doing the differentiation on the left-hand side, of course, minus E gamma mu, the well-known derivative of P slash with respect to P mu, B equals C gamma mu. Thus, B and C are connected in exactly the way our other arguments said they would be connected. They're proportional to each other by a factor of E. This is much more complicated than the other way of doing it. Nevertheless, it's reassuring to see it done the other way. And it also tells us something else that the other way didn't tell us, for all my pride in it, and that is that we could do the same thing. We'd obtain exactly the same relationship between the two counter terms if we didn't normalize our at 0 for the electron, but put the electron on mass shell. If we put the electron on mass shell and defined our coupling constants that way, the corresponding equation would be S of P slash equals A plus P slash minus M B plus order P slash minus M quantity squared. We would find, and of course a corresponding equation for gamma mu in power series in P slash minus M. We would, of course, find exactly the same thing by applying this Ward identity, now not at P slash equals 0, but at P slash equals M. The differentiations are step-by-step the same. So we can preserve our subtractive procedure even if we put the electron on the mass shell, rather than putting it at the BPH point, zero momentum transfer, we still have a perfect matching between the counter terms required of the charge renormalization type and those required of the electron wave function renormalization type. On the other hand, very important point, even if the photon has a mass, you've still got to keep the photon at zero momentum transfer, because this equation is true only when this thing is zero. We can, with no loss, in perfect matching of the counter terms, keep the electron on the mass shell instead of at the BPH point. But the photon, whether it's massive or massless, has to be kept at zero momentum transfer to get that perfect matching. Of course, the divergent parts of the counter terms will still match, since the question of what infinities you have to add to the Lagrangian to get infinities out of the answer will, to purge the answer of infinities, is independent of what subtraction point you use, how you parameterize this theory after you've gotten rid of the infinities. But in general, the finite parts of the counter terms will be different if you have a subtractive renormalization scheme where all the particles are in the mass shell unless the photon has mass zero. Are there any questions about these points? I went through this rather hastily, but this is pretty much standard material, not the derivation of the equations, but the subsequent exploitation of them. Yes, sir? On the photon. The charges defined that way would not be equal. If we had a theory with a massive photon, okay, and if we defined the photon-proton coupling to be the 3-point IPI function with all particles on the mass shell, and the photon-electron coupling to be the same thing with all 3 particles on the mass shell, then equality of the bare charges would not apply equality of the physical charges, defined that way. The massive photon. If, on the other hand, the photon is at zero momentum transfer, use the same definition, but the photon is at zero momentum transfer, whether it is massless or massive. Of course, if it's a massless photon, zero momentum transfer is the mass shell. The two definitions are the same. Then equality of the bare charges implies equality of the renormalized charges. Thus, some people, this has definite physical consequences. Some people like one time, J.J. Sakurai was very strong on this. He said the rho meson was just like a photon, except it was heavy, and it coupled to the isospin current rather than coupling to the electromagnetic current. Let's take the rho naught, couples to the IZ current, aside from the I3 current instead of coupling to the electromagnetic current. And it had a strong number. Instead of 1 over 137 as the square of its coupling constant, the square of its coupling constant was on the order of 1. Otherwise, everything he said was exactly the same. It was minimally coupled theory, certain complications caused by the non-abelian nature of the isospin group. Let's take the omega. He wanted that to be coupled to a hypercharged current. Okay. Does not non-abelian, exactly the same. You've just got 2 photons, one which is strongly interacting and heavy and called the omega, and one which is weakly interacting and massless and called the real photon. Otherwise, everything is the same. And therefore, you get universal omega coupling, just like you get universal photon coupling. Okay. But you get universal omega coupling when the omega is extrapolated to zero momentum transfer. That's a 1 BeV, or 0.8 of a BeV, extrapolation, okay, which is a long extrapolation for the strong interactions. That's a long way off mass shell. Hard to get to. So the idea was sort of hard to check, even if you could compute the omega so-and-so, omega lambda k, or omega kk bar, and omega proton, nucleon coupling constants, which is not easy. Omegas are not particularly stable particles, but well, they're more stable than most. You can do experiments with them. Even if you could compare these things and you found they were 40% off one from the other, Sakurai was still happy and would smile a lot while he would say, oh, that's just the error you make because you're extrapolating from a physical omega on the mass shell down to zero momentum transfer. Okay? So if you have a really heavy photon, the consequences on physically observable quantities are hard to check. unless, of course, the coupling constant is weak, whereupon you can check everything by doing perturbative computations. And such perturbative computations are what we shall do next lecture, when I will finally get to the anomalous moment of the electron.